Yeah, so
all right.
if everybody's okay, we're going to start recording.
All right. Is my screen shared?
Yeah.
People seeing my slides? All right. Shall
Okay, so everybody, welcome to the first seminar, or 2021. It's going to be Branimir Ćaćić from the University of New Brunswick, Fredericton in Canada, and it's going to talk about building blocks for gauge theory on quantum principal bundles.
Thank you very much, Ray. Thank you for the opportunity. And well, Happy New Year, everyone. Hope you're all taking care and you're all staying safe. So this is a caveat, brand new talk on material I'm writing up, and it's the first week of classes. So this is, bear in mind, this is going to be rough. This is going to be really rough. So I beg your forgiveness in advance. So this is, in the interest of shameless self-promotion, this is based on work in progress. Not in progress, in preparation. Our arrival in the archive is within is going to be within a matter of a month or two. But if you want to do things, if you want to work with quantum principal bundles over compact connected Lie groups with the de Rham calculus and do everything in spectral triple land, you can do everything in spectral triple land to degree 1, and that's worked out in this monstrous preprint with Bram. So if you're interested in spectral triples and unbounded KK theory, and the sort of compact connected Lie case, take a look at that. The hard analysis done here. So in some sense, what I want to talk about, this work here arises from basically an effort to sort of take all this misery and try to distill down, like, okay, what the hell's going on at the level of just honest to God, different, first order differential calculi on the underlying algebras, like just what's going on at the level of sort of the algebraic gauge theory on the algebraic quantum principal bundles, underpinning everything. And so in this sort of the first section, I'm going to give you a sort of semi-polemical, not particularly illuminating whirlwind introduction to what quantum principal bundles are in the conventional sense, and then I'll indicate the point of departure. And the main reason for the departure is that when you're working in spectral triple land, you're concerned with first order differential calculi. And you find yourself in a situation where the object that ought to correspond to a principal connection, the object whose varying gives you a variation of the principal connection, leads to non-isomorphic total first order differential calculi, which seems really, really freaking weird. But as I hinted at in the abstract, I hope to convince you that this is a feature and not a bug. Okay. So let me just set some preliminaries for the sake of, here's some preliminaries for the sake of setting notation and terminology. Our structure group, our structure quantum group, will always be some co-semi-simple Hofstar algebra H, or if you like, compact quantum group algebra, I think is the jargon. Another caveat, I come from spectral triples land, and I've been learning the sort of algebraic stuff, so I'm probably going to screw something up every 2 slides. So please, there are experts here, please bear with me. So H should you think of as the analog of your compact connected Lie group. H in particular will be this algebra of, in that case, will be the algebra of matrix coefficients. And then the analog of a topological principal bundle will be something called a principal left H comodule star algebra. So it's a star algebra with a nicely behaved left H coaction, which corresponds to your group action. And then you have this condition where this canonical map from P tensor P to H tensor P, defined in this fashion using Swedish notation. So this represents the coaction of H on the element P. This lives in H, this lives in P. This canonical map from P tensor P to H tensor P is a surjection. So that's, if you're in this regime where you're co-semi-simple, that's what it amounts to. And I think it's a non-trivial proposition of various people.
Sorry, I'm going to stop you. So for what I would have, this should be an isomorphism if it's the Hopf-Galois.
This is a tensor product over C.
Okay, so that was going to be my next question. So that's not a typo. It is genuinely a product over C.
A product over C.
Okay.
So we have this principle. So So when you're co-semi-simple, where you're in this regime that includes, group algebras of discrete groups, and includes, basically your compact Lie groups, the sort of algebraic distillation of principality boils down to this by the work of various people. And so if P is your algebra, let B be the subalgebra of co-invariants. That's the analog of the base space. So P is the non-commutative total space, B is the non-commutative base space, H is the structure group. So if you sort of start unpacking what's going on in terms of sort of philosophy, this means that the H coaction is topologically free, CF Elwood, CF, the recent paper with Baum-de-Kommer Hertz. And there's a sense in which it's vestigially locally trivial to the extent that your quantum associated vector bundles really are finitely generated projective modules. And
I'm sorry to disturb. I agree with Ramon. The Kern is not a tensor. Isn't that a tensor product over your base?
No, it's over C.
Yeah, that's what confuses.
So when it descends to a bijection.
Oh, okay. So
it descends to a
canonical is not a bijection, of course.
It's a surjection. So when it's a tensor over C, it's just a surjection. But
okay,
then
sorry about
no, it's all good. Okay. So I'm trying. So if you don't. So I'm trying to write this sort of definition in as simple a manner as possible. If you ditch this co-semi simplicity, then you want the map from P tensor over BP to be a bijection, and then basically you want the existence of a universal connection. But that's another story. But basically what I want to say is that this is a good notion of being a topological quantum principal bundle. You have topological freeness in a way that it sort of dovetails perfectly with what Elwood observed in the case of C-star algebras, the topological category. And there's enough vestigial local triviality that your quantum associated vector bundles are actually non-commutative vector bundles. And so this is so you can really justifiably call such a beast a quantum principal bundle at the topological level. So the principality is topological. I'm not claiming anything about differential calculi yet. So what's the game? So let's fix a differential calculus on the base. Fix a first order star differential calculus on the base. And let's fix a bicovariant first order differential calculus on the structure group. So if you have a regular compact Lie group, then this is just the first order de Rham calculus. And so the naive goal is to find all lifts of the calculus on the base to calculi on the total space that satisfy the things you'd want. So what's the naive goal? You want to find all left covariant first order calculi on the total space, such that on the one hand, it really does restrict to the calculus on the base. So you have basically an isomorphism of the calculus on the base with this subcalculus generated by B, such that when you take the image of one forms in the base and form the P sub-bimodule generated by that range, then the co-invariants are precisely those guys. So if you like, the invariant horizontal one forms are basic. That's what you want. And the second thing is you want P together with this calculus to define a quantum principal H bundle with this not necessarily universal calculus with respect to this not necessarily universal bicovariant calculus on H, emitting a star preserving bimodule connection. And so if you sort of unpack this further, what does this actually mean? Well, you have this bimodule, sub-bimodule of horizontal one forms, including into here. You have this sort of vertical map from the total one forms to left invariant one forms in H tensor P, given basically by taking a sort of orbit-wise derivative. So all this is an abstract version of contracting a one form on your total space by the fundamental vector fields coming from your Lie action. And so what you want is for this to be not just a short exact sequence of left H covariant P star bimodules, but you want it to be split in that category too, and a left splitting is your star preserving bimodule connection. So where does that take you? So since we're asking for the splitting to be really a splitting of a short exact sequence of bimodules of, in a way that preserves the star structure and that preserves the H coaction, what a left splitting gives us really is a decomposition of this total calculus into a direct sum of a vertical calculus and a horizontal calculus. So the vertical calculus is basically just taking, is what you get by differentiating elements of P orbit-wise along this, using this orbit-wise differential calculus, this bicovariant differential calculus on the structure group H. And then what is the horizontal calculus? It's, well, it's basically this lift of the basic calculus that you get by just projecting down to the horizontal one forms. And if you hone in on this sort of horizontal calculus, this really does restrict in the appropriate way. It's really is a nice projectable horizontal lift of the basic calculus. And one other thing to note, this condition here, by a lemma of Beggs and Majid, this left splitting of the short exact sequence isn't just a connection, but it's a strong connection in the sense observed by Hayat. So people in a lot of contexts like to look at strong connections in particular. Where does that strong connection condition that you've seen sort of morally come from? It really actually is it's the underpin, sort of what's really going on is this. What strongness really is telling you is that the co-invariant horizontal one forms are precisely the basic one forms and none other. That's what the strong condition tells you.
I'm going to, so for me, it to be a strong connection, it means that you've just got, well, in this, as you have it, P omega 1 of B by P, that basically once you apply D to, what is it, to P in your case, then you'll just land in, and you project. You just get the P's on one side, depending on what side your covariance is. Is that that's what you were saying?
Yes, exactly.
Yeah, because you have the P's on both sides by definition, and you want to pick just, okay, sorry, I just wanted to check.
So the strong business is saying that you can get away with P just on the one side.
Yes, okay, good. So we're on the same page. Thank you.
So I think what I point out is that this is more fundamental. But that's a polemical statement. So this is all well and good, but what I really want to do is sort of hone in the problem and sort of specialize a little bit. So I propose a sort of refined goal coming from a change of perspective. So what I want to do is say the following. So let's suppose we have, and so this change of perspective is coming from the business with spectral triples and unbounded K theory. So suppose we have such a covariant differential calculus in the total space. Let's fix the subbimodule of horizontal forms. Let's fix this identification of the one forms in the base with the co-invariant horizontal one forms. And let's fix an identification of the one form of the total one forms with a direct sum of vertical one forms and horizontal one forms. And so in particular, what I want to do is I want to fix this vertical map, this contraction with left fundamental vector fields. So I'm going to let the actual differential vary, but I'm going to fix the calculus on the base. I'm going to fix the calculus on the orbits. I'm going to fix this bimodule of horizontal one forms, and I'm going to fix the way, I'm going to fix the bimodule of one forms, and I'm going to fix the contraction of one forms with fundamental vector fields. So what I want to do is I want to find all derivations from P to one forms such that that are lifts of the derivative on the base, and that give you a quantum principal bundle whose that has the right contraction by fundamental vector fields and that admits a suitable connection. And so let's unpack what this means further. Well, if you use this business here, this actually simplifies down to something very, very simple. All we're doing in this case is finding all h-covariant star derivations from P to the horizontal one forms that define lifts of the derivative on the base. That's all we're finding. And what I want to point out is that this refined goal doesn't involve the orbit-wise geometry one bit. So we've sort of decoupled things. We have stuff going on along the orbits. We have stuff going on horizontally. And what I want to sort of the perspective I want to emphasize is that the projection is the connection is sort of what glues the vertical geometry and the horizontal geometry together. That's something you can make precise in spectral triple and unbounded KK theory land. This is sort of how it manifests at the level of differential calculi. So this was all kind of miserable, but what I want to now do is sort of start at the very beginning and build things up from there. So what I want to do is just start with the first order calculus on B and slowly, in this very conservative fashion, build up to a suitable total calculus on the total space that does what we want it to do. So let me begin with a little convenient implicit folklore. So let E be a B star bimodule, and the star means that you have this conjugate linear involution of E that basically formally acts like the star operation on the star algebra. So it'll be convenient to really think systematically what it means to lift a B bimodule upstairs in a horizontal fashion. So here's something that's really implicit in all sorts of literature on sort of the differential and Riemannian geometry of principal bundles. Let's say that a horizontal lift of E is a pair E tilde iota, where E tilde is a P star bimodule, and where iota is an inclusion of the B star bimodule E into the co-invariance of E tilde, such that E tilde is generated by the image of E. And we'll call this lift projectable whenever the co-invariants are precisely the image of E. And so that this lemma of Beggs and Majid I alluded to in the recent, it's sort of buried and written in a slightly different way in a special case in like chapter 5 of the recent book, but it's basically saying that a horizontal lift is projectable if and only if E tilde can be written as P times iota of E. So for me, a choice of bimodule of horizontal one forms is a choice of horizontal lift of the bimodule of one forms on B. But now we have this lifting process. You can ask, okay, what are the symmetries of this lifting process? So let's define an automorphism of a horizontal lift to be a pair phi star, where phi is just a covariant star automorphism of P that is the identity on B, and where phi star basically is a lift of phi to E tilde that satisfies phi star composed with iota is iota and does the thing that you expect. And so these form a subgroup of the automorphisms of the automorphisms of P times invertible complex linear maps on E tilde, which we denote like this. So this is a subgroup. These are the automorphisms of the horizontal lift. And what's nice is that because of this condition, and because of the fact that E tilde is generated by iota of E, your automorphism is completely determined, uniquely determined by phi. So we can just view this automorphism group as a subgroup of the automorphism group of P itself. So let's just now apply this to the case where E is omega 1 of B. So let's fix a calculus on B, and let's fix a projectable horizontal lift, omega 1 P horizontal iota of omega 1 of B. So a gauge transformation simplicator we'll define to be an automorphism of this horizontal lift, and we'll write math frac G for this automorphism group, and we'll define a gauge potential, principal connection, to be a lift of the derivative on B to a covariant star derivation from P to the horizontal one forms. And we'll denote by math frac at for Atiyah the set of all these gauge potentials, because lurking in the background, there's this sort of observation by Atiyah that principal connections are splittings of a certain short exact sequence of equivariant vector bundles. So parenthetically, why the focus on gauge transformations? Well, one of the sort of technical challenges that keeps on, one of if you look at the literature, at least naively, like I have been, you look at the literature on quantum principal bundles, there seem to have been real technical challenges with making sense of gauge transformations. You can do it in the universal case, and then you can weaken things in various directions because there often aren't enough of them. But trying to adapt it to the presence of some non-universal calculus seems to be a persistent challenge, and the closest, as far as I know, that anyone's come to tackling it head on is the unpublished thesis of Zuka, to which I'll refer again. But if nothing else, here's a convenient sort of starting point. We're talking about gauge transformations. It's just an automorphism of this lifting of one forms of the base to horizontal one forms on the total space. And note that this gauge group acts on the space of gauge potentials in the silly obvious way. So here's your baby gauge action. So this would all be kind of silly if there weren't extra structure on this space. From the classical case, you expect this to be an affine space, and indeed it is in a sort of natural way. Let's define a relative gauge potential to be a covariant star derivation from P to the horizontal one forms that vanishes on P. And now the moment you have a gauge potential, the set of all gauge potentials is automatically going to be an affine space with space of translations, the space of relative gauge potentials, just by literal subtraction of maps into this vector space. And then this gauge action on the space of gauge potentials is going to be affine linear, with linear part the obvious action on the space of relative gauge potentials. So to illustrate, so this is all kind of banal, but to illustrate this, let me give you a quick example. Nothing earth-shattering here, but worth thinking about. So suppose you have a discrete group gamma, and suppose that M is a compact gamma manifold. So let H be the group algebra of gamma. Let P be the algebraic cross product of C infinity of M by gamma with the canonical H coaction. And by abuse of notation, let take your horizontal one forms on P to be the cross product of the one forms on the base M by gamma. So you have a tensor product, and then the left multiplication and right multiplication are related by the gamma action on the one forms. And so you can sort of turn the crank, and what you find is actually kind of nice. There's a canonical gauge potential, which is the silly thing. You basically form the obvious extension of the derivative on the base, and that gives you an honest gauge potential. But what's really interesting is when you look at the relative gauge potentials in the gauge groups, the relative gauge potentials are literally one cocycles on gamma with coefficients in the real one forms on M. And there's an explicit map with an explicit inverse. And what's extra nice is that you can ask, okay, what are the co-boundaries? Well, the co-boundaries are the derivations in here that are inner. And then similarly, the gauge group has an interpretation as a group cohomology gamma with coefficients in this abelian group. You can work it out explicitly as well, and you can work out what the gauge action is. It has trivial linear part, and then the gauge group acts on this canonical gauge potential in this very, very simple fashion. You can push this further, quite a bit further, to more or less general H. Then co-boundaries become a little weird to discuss. This becomes a little weird. And I'd be interested to know, this is something that's puzzled me, in any concrete example I can come across, this action is trivial linear part. So I'd be curious to find an example where you have non-trivial linear part. So nothing particularly earth-shattering here, but it's still interesting to observe that fairly natural group cohomology can be viewed as gauge theory. So you may be wondering, okay, that's just a horizontal piece of the action. What about the total? What about the whole? So in the next section, I want to bring back in the orbit-wise geometry and see what happens. So before I continue, are there any questions or barbs or rotten tomatoes? Or shall I proceed? Okay. Hearing none, I will continue. So far I've been babbling about the horizontal part of the calculus, but to have a total calculus on the total space, you need to account for the orbit-wise sort of geometry as well. So let's introduce some choice of bivariant calculus on H. And let me just note that I think this is an observation, I think, going back to Majid. You can completely determine this calculus in terms of its quantum Marat-Cartan form. So if you can take the left H covariant one forms, these form a left cross H module in a natural way. This is what the H action is, or a Radford-Jeter-Drinfeld module. There's a lot of jargon out there that confuses me. And then you can completely encode what the differential on H is in terms of the resulting quantum Marat-Cartan form, which is given like this. And this is now going to be a surjective.
Probably from Voronovich. This is before Shan.
This is Voronovich.
Yeah.
Okay, this is due to Voronovich then. So so now you have this quantum Marat-Cartan form, which is a surjective unitary one cocycle valued in this thing. So the cocycle condition, when you're working with quantum groups, looks like this. And now unitarity means, okay, you still have the star operation that persists here, and then this cocycle respects the star operation in this fashion. So really, this is saying that this is, I feel like, a real valued one cocycle. So given this, you can now start building, if you like, looking at the orbit-wise differential geometry. So we can form, if you like, it's really the dual bundle of the vertical of sort of the orbit-wise tangent bundle of P as a sort of H manifold, if you like. So let's define the vertical one forms to be left invariant one forms in H tensor P, which we can. So this has a natural left H coaction. It has a natural right P module structure, but it's actually a covariant P star bimodule. So what's the left action? Well, the left action works like the left module structure works like this. If you have Q, an element of P, you can bring it past var pi of AH by doing the natural thing. The price you pay is that is the thing that you expect, and then you have no choice but to define the star structure in this fashion. And now now you have a nice covariant P star module, and now you can make perfect sense of the vertical derivative, which looks like this. So basically, in the classical case, you're literally just taking the orbit-wise derivative of your function. And so now it makes sense to say that your bivariant calculus in H is locally freeing whenever this bimodule is actually generated by the range of P. In which case you really do get a differential calculus, which you can call, if you like, the vertical calculus. So if you like it, when you unpack it in the commutative case, it really is local freeness. So given this, let's see what happens when we smash this together with the horizontal calculus. So let's fix a projectable bimodule of horizontal one forms such that we have gauge potentials. Let's take a locally freeing a bicovariant calculus for H, and let's put Humpty Dumpty back together again. Let's set our total one forms to be the vertical one forms, direct sum the horizontal one forms. and let mathfrak D be the set of all covariant derivations that do the job. They're lifts of the derivative on B, and they give you a quantum principal bundle with the appropriate properties. And now it's not hard to sort of piece everything together and see that you have a bijection between this affine space of gauge potentials and this set of differentials in this fashion. If you start with nabla, you get the total derivative by taking this direct sum. So this is all well and good, but now what you really should be asking yourselves is, okay, how many isomorphism classes are there? Are all these things giving me an isomorphic covariant differential calculus on P? Or are there distinct isomorphism classes? And can I parameterize, is there some moduli space of isomorphism classes? So let's define the obvious equivalence relation in mathfrak D. Let's set D and D prime to be isomorphic whenever the corresponding covariant first order calculi are isomorphic. And then there's an easy but somewhat startling proposition you can prove, that for any relative gauge potential, the following are equivalent. For every gauge potential, the total derivative you get corresponding to nabla plus A is isomorphic to the total derivative you get just from nabla. So perturbing nabla by A doesn't change the isomorphism class of total calculi. Second, there's just some gauge potential nabla such that perturbing nabla by the relative gauge potential doesn't change the isomorphism class of the total calculus. And here's where things get interesting. The third equivalent condition is basically that this relative gauge potential is given by a relative connection 1 form, that you can find a morphism of covariant P-star bimodules from the vertical 1 forms to the horizontal 1 forms, such that A is just your connection 1 form composed with a vertical derivative. And in this case, this relative connection 1 form is unique, and actually these isomorphisms are unique as well. So we can let frac at of omega 1h be the set of all such relative gauge potentials. This turns out to be a gauge invariant subspace of the space of all relative gauge potentials. So this is nice because now we have life is pretty good in this easy warm-up sort of degrees 1 situation. If you go back to this parameterization of the space of the set of all suitable total derivatives by mathfrak at, you can check this is gauge equivariant, that this you can check that this equivalence relation is gauge invariant in the suitable fashion. And now you have a baby version of a more complicated theorem that says that this quotient affine space parameterizes basically these suitable total calculi up to isomorphism via a certain very explicit bijection. So this is nice. You have the nicest conceivable moduli space. It's just an affine space. So you really can understand what's going on here. So I call this a baby theorem because it's easy in degree 1. It becomes hard in degree 2. So maybe let me pause here. This is what basically what I want to talk about in the degree 1 case. I'm going to spend the rest of this time seeing how much I can say about the degree 2 prolongation and curvature. So before I continue, are there any questions or comments or corrections? Okay. If not, let's actually, there was one last point I wanted to make relating to Zulka's PhD thesis. So I commented earlier that there seems to be this very basic technical difficulty of understanding what it means for a gauge transformation of a quantum principal bundle to actually be to actually respect some sort of non-universal differential calculus. Well, I claim that here we have a pretty good candidate for what that should mean. So let's suppose we have the suitable total derivative, which must therefore come from some unique gauge potential. we have this natural action of the gauge group on the space of total calculi. Basically, you conjugate your total derivative by phi, and that's what happens. It's sort of just the obvious thing. And so you can define the gauge group of your particular differential calculus to be the stabilizer subgroup of that differential calculus up to isomorphism of total calculi. And so now we have a cute little corollary. It's actually pretty banal, but it's nice to write down all the same. Because of that bijection that we had, this abstract looking gauge group is something very, very concrete. It's the group of all gauge transformations such that the difference between the corresponding gauge potential nabla and its action and nabla acted on by phi is one of these sort of special adapted sort of classical type relative gauge potentials. And then if you want to know what the actual, if you like this sort of immediate gauge theory of this thing is, if you want to restrict yourself just to calculi that are isomorphic to this particular calculus, then you can parameterize that, then you can parameterize everything and hence by sort of change of perspective, all the bimodule star preserving connections by this affine subspace in the obvious fashion. And so what I want to observe is that this strange business up here actually generalizes a definition proposed in Zuka's PhD thesis. So if there's any moral to this story, I'd say that there's a lot of, you can gain a lot by really looking at allowing the total calculus to vary and then looking at what it actually means for different calculi to be isomorphic as calculi. And so it's the symmetries of this lifting process that give you the gauge group, and it's a and it's looking at isomorphism of total calculi that let you really sort of refine things down. So that's the first order theory. It's not enough to talk about curvature. So what I now want to do is talk about a certain very sort of economical sort of second order prolongation of everything that'll let us talk about curvature. And one thing I do want to sort of maybe want to emphasize, if you're coming from spectral triple land, there is a differential calculus called the Duran calculus of the spectral triple. It's nice to write down in degree 1. You can hack it in degree 2, and it just becomes agony beyond that. So if you really want to work with spectral triples, you really want to have a notion of curvature that doesn't depend on having a whole exterior algebra. You want to be able to get away with no more than degree 2. And you want to be able to do this as sort of economically as possible. Another problem is that when you start with a first order calculus and do your favorite, and say a maximal prolongation, you're invoking the particular choice of derivative. So if you want to let the derivative vary in a certain way, albeit a controlled way, we can't just take maximal prolongations to compare and contrast and see what curvature is. We have to do something a little more finicky. So let me conclude by talking about curvature. I think I won't have time to talk about any further examples, but I'll happily mumble about things if people ask. So let's set some convention. So as a simplifying convention, I only care about things up to degree 2. So everything is mercilessly truncated at degree 2. Degree 3 is 0, et cetera, et cetera. I don't care. I just want 0, 1, and 2. So to set some terminology, I just want a convenient notion of what it means to extend a derivation from 0 forms to 1 forms to an entire calculus. So let omega be your favorite covariant non-negative integer graded star algebra. Suppose we have a derivation from 0 forms to 1 forms, from degree 0 to degree 1. Let's define a prolongation to be a degree 1 extension, an extension of this beast to a degree 1 derivation of the whole. That's just the sort of the obvious thing, but let me just set the notation. So what we're going to be concerned with is sort of the easiest thing you can do is actually just focus on the horizontal piece of the picture and look at prolongations of gauge potentials and relative gauge potentials. So that's what we're going to do. Let's just fix an exterior calculus on B. Again, I don't care about anything beyond degree 2. Let's take a sort of a projectable horizontal lift of this calculus to rather of the graded algebra of forms to a graded algebra of forms over P. So if you like, you'll have P horizontal 1 forms and horizontal 2 forms. And then the horizontal 2 forms will still be a projectable horizontal lift of the 2 forms on B. You'll have a wedge product that makes everything work out, et cetera, et cetera. So when are the different sort of ingredients we've been concerned with sort of compatible with this prolongation? Well, let's say that a gauge transformation phi is prolongable whenever it admits a necessarily unique extension to an automorphism of this algebra of horizontal forms, and let this be the subset of all prolongable gauge transformations. Let's call nambla a gauge potential prolongable whenever it admits a necessarily unique prolongation that restricts to the derivative on the base. And so let this be the set of all prolongable gauge transformations. And then similarly, we can call a relative gauge potential prolongable whenever it admits a necessarily unique prolongation that vanishes on the differential forms on the base. And you can let this denote it's the subset of all prolongable relative gauge potentials. So once you do this, all the pieces fit together into a nice way. This will be a subgroup, and this will be a prolongably gauged invariant affine subspace with spacer translations. This guy. There's nothing really exciting here. It's just a simple algebraic observation. But what's nice is that you can now talk about curvature and relate it to the ability to form in some sort of uniform fashion a prolongation of the total calculus. So once you have all this, what's curvature? Well, curvature is basically, if you have a prolongable gauge potential, you take the prolongation squared. And that is completely determined, but it maps P to horizontal 2 forms and it kills everything else. And now it has some nice basic properties. This curvature actually turns out to be a covariant star derivation that vanishes on the base. So morally, you expect it to be some sort of vertical first order differential operator. And moreover, if you think of the curvature as a map on this affine space of prolongable gauge potentials, it's a quadratic map. It's an affine quadratic map, and it's equivariant with respect to the gauge. It's with the suitable subgroup of the gauge group. So everything is nice. Everything works out exactly as you expect. So far, nothing really particularly interesting has happened. Where interesting things actually start happening is when you try to really piece together a total calculus through degree 2. So that's sort of the big punchline of today. Let's now introduce a locally freeing bicovariant calculus on H, and now let's bootstrap. We can now piece together a total algebra of differential forms in the total space through degree 2. So in degree 1 we have P, in degree 0 we have P, in degree 1 we have our usual 1 forms, vertical forms, direct sum horizontal forms. And then we can generate degree 2 as follows. We impose what the quantum group specialists will recognize as a superbosonization relation, I believe it's called, on a product of 2 left covariant 1 forms in H, thought of as vertical 1 forms. So when you're just dealing with a classical sort of compact group, this is just saying that 1 forms anti-commute. You impose a relation relating vertical 1 forms and horizontal 1 forms. So how do you relate the product of a vertical 1 form and a horizontal 1 form, where you impose again a kind of modified anti-commutation, taking into account the fact that this module this, you have actually cross module of left invariant one forms in H looking around. It's accounting for this H action on these guys. And then you have whatever relations generate the horizontal two forms for the horizontal one forms. And so you piece everything together, and what it looks like, you basically have purely vertical two forms, which are, you know, all the products of vertical one forms with vertical one forms. You have these sort of mixed vertical horizontal two forms. So these are products of vertical one forms with horizontal one forms, and then you have the purely horizontal two forms. So given all this, you can now ask, okay, when can I take, given a prolongable gauge potential, it gives me a total derivative from P to the one forms, when can I get an actual honest to goodness derivative from one forms to two forms that satisfies d squared equals 0?
Branimir,
Please.
a short, silly question.
Please.
Am I right that it's more or less look like that? You take some maximal prolongation of your horizontal forms, vertical forms, and then take some braided tensor product of these two prolongations?
I believe so.
Okay.
I mean, like this is, so yeah, this is just yeah, this is the like the sort of super bosonified prolongation of the vertical one forms. This is whatever prolongation of the horizontal two forms you started with.
Okay. Yeah.
But then you have to do something. You have to decide what happens when you take a product of a vertical one form with a horizontal one form, and so you impose these extra conditions.
Yeah. Good. Okay. Thanks.
So it's I guess it's like a braided anti-symmetry, right?
Yeah, it looks like a braiding for Yetter-Drinfeld.
Yeah, again, I'm a noob to all these things, so but this is what I vaguely gather. So thank you for the clarification.
Okay, thanks.
So if you have this, you can ask, okay, let's get a DGA. How do we get a DGA? Well, here's our first interesting fact. Suppose we have a prolongable gauge transformation. The following are equivalent. On the one hand, you have a prolongation of your total derivative from P to one forms that satisfies the magical condition d squared equals 0. And on the other hand, what's the equivalent condition? That you can, that the equivalent condition is that the curvature really is an honest to goodness vertical, first order vertical differential operator. There's a horizontal two form valued vertical one form, Lie valued one form. You have a morphism of H covariant bimodules, bold phase capital omega of nabla from the vertical one forms to the horizontal two forms that lets you write your curvature of nabla like this. In which case, this prolongation is unique, and this Lie valued horizontal two form is unique as well. And so if you're in this case, let's define the set of all such, so if you like totally prolongable gauge potentials to be this, it's actually gauge invariant in the suitable sense, gauge invariant under the appropriate subgroup of gauge transformations. And you can actually write down quite explicitly what the total derivative from one forms to two forms does on the quantum Marrer-Cartan form of H. What does it do? It does the usual derivative in whatever your favorite calculus on H of this invariant one form minus, you know, curvature two form contracted with this one form. And then what does it do to horizontal one forms? Well, there's an obvious analog of vertical differentiation, and then you have the prolongation of nabla that differentiates the horizontal direction. So this is a totally vertical piece. This is a totally horizontal piece. This is a mixed vertical horizontal piece, and this is a totally horizontal piece. And so now with all this, again, you run into this basic question: when are my calculi isomorphic or not? And if I have different isomorphism classes, is there a nice moduli space? So let's pose the problem precisely. Let this be the subset of all prolongable total derivatives from P to 1 forms that satisfies those conditions we cared about to begin with, except now they're prolongable in the sense that you have a prolongation that satisfies d squared equals 0. We still have a gauge equivariant bijection from these special totally prolongable gauge potentials to these special prolongable total derivatives or prolongable calculi. And now there's an analogous refinement of our equivalence relation of sort of isomorphism of calculi, where you just now require the isomorphism to cover the entire calculus through degree 2. And so you can now ask, okay, what are the isomorphism classes? What are the isomorphism classes of calculi now that you account for degree 2? And this now gives you a real theorem, I hope. So let's suppose that A is a prolongable gauge potential. There's a little PR missing. Then the following are equivalent. First, for every totally prolongable gauge potential, the perturbation of nabla by A is still totally prolongable, and the second order calculi are isomorphic. Second, there exists one totally prolongable gauge potential such that the perturbation is totally prolongable, and the resulting calculi are isomorphic through degree 2. And third, this gauge potential is given by a relative relative connection 1 form, whose range such that the image of your left invariant 1 forms on H under this, such that the contractions of your relative connection 1 form with left covariant 1 forms on H supercommutes with the 1 forms in the base, and such that the images of left covariant 1 forms on H under this, the contractions of left covariant 1 forms on H with this relative connection 1 form satisfy the appropriate sort of super bosonized, this sort of braiding relation, the super braiding relation. And then moreover, this is also a little not obvious. The moment that there exists one such one of these guys, the moment the set is non-empty, then the set of all such relative gauge potentials is actually a linear subspace. It's a gauge invariant linear subspace, and that it's actually a linear subspace is not obvious. This is homogeneous, so you're preserved under scalar multiplication, but that it's linear requires this actually. So this is actually kind of striking, because it now means that the moduli space we're seeking is actually a quadratic level set. So this is my punchline, for such as it is. Suppose there exists a totally prolongable gauge potential, then we have a nice moduli space of all of these sort of prolongable total calculi up to isomorphism, and it's given by a certain gauge invariant affine quadratic level set in this affine space. And what's the bijection? It maps the affine subspace of your connection, a gauge potential nabla, to the isomorphism class of the corresponding total derivative. So what I want to say is that despite all the sort of silly generality, which for the most part results in, to be honest, banalities, there's still some interesting things happening. You've got a moderately interesting moduli space that you can actually write down. And note in particular that each of these isomorphism classes are still affine spaces. So I think that's all I want to say. That's all I really should say. I'm 5 minutes over. Thank you for your attention and your patience.
So are there any questions in the audience? Andre, or Ray might have one if he gets back to his computer. I just saw him zoom by to go to the washroom.
Well, I'd like to say first that was a really, really fascinating talk, because this whole idea of gauge theory, I think, is really important. I'll say a very quick remark about why is because one thing that's always fascinated me is Kahn's standard model is really fundamentally a quantum field theory model, but it ought to have an underlying classical model, and that classical model ought to reflect a lot of the structure of the quantum field theory. And to do that, that's really a non-commutative gauge theory, and so progress in that direction, I think, is really, really important. And the other geometric thing I noticed, whenever you had the curvature, you had a subgroup coming in, and that classically looks very reminiscent of holonomy, where you start off with a group for a bundle, which it turns out is unnecessarily large, and somehow a holonomy construction gives you a sort of a minimal group that you really needed to have. Anyway, 2 random observations. But anyway, it was very, very nice. Thank you.
Thanks, Edwin. And I have to say, this would have been impossible without the book. The book was my vademecum. So thanks for the book.
Thank you.
Yeah, okay, so maybe Branimir, thank you. Nice talk. I'll ask a question. So
Please.
The usual one with this, the old chestnut, is what happens when you try to apply it to Padlet?
That is yet to be determined. So let me say what's so in the preprint we'll talk about basically the cleft case, and we'll talk about so basically when you have a non-commutative 2 torus where theta is a real quadratic irrationality, then these Heisenberg bimodules actually give you a canonical quantum circle bundle. And what's interesting is that you can realize these canonical constant curvature connections, and this family of holomorphic observed by Cohn way back in the early 80s, as well as like all these additional holomorphic structures observed by Polishchuk and Schwartz, as giving you the gauge theory of this quantum circle bundle. But the plot twist is that you can't use the de Rham calculus on the circle. You have to Q-deform it, where Q is the fundamental, the norm positive fundamental unit of the quadratic field. Number theoretically, this is probably quite banal, but I think this is going to. I think this may be like it's some sort of moral evidence of what you might suspect, what you should expect to be able to deal with if anyone should follow up on Sasha Peterka's suggestion that you should be able to construct a U1 instantons on S4 theta. So if you can get weird shit happening on just for this otherwise relatively this utterly unassuming, circle bundle over a quadratically irrational non-commutative 2 torus that's been hiding in plain sight since the early 80s, then you could get sort of non-commutative phenomena that you normally associate with the Q-deform situation happening even on the non-torus equivariant side, sort of non-torus equivariant geometry of these sort of theta deformed spaces. I'm working with my PhD student Karthik Timavajula to work out what this looks like for something like S3 theta over CP1. So, or more generally, if you have a circle bundle over commutative base that's has finite strong local triviality dimension in an algebraic sense, a la all the people, some of whom are here, I believe, and you get a sort of cohomological picture there. As for podlesh well, the Q monopole is going to be an element of mathfrak capital at.
Mm-hmm.
What else lives in this affine space, I don't know. And what lives in the gauge group, I don't know. And I also don't know what happens when you move up to, when you try to play this game at the degree 2 level. I don't know. That's probably a big project.
Yeah. Okay, but I guess the examples that you're really working with are the ones that are motivating this, or theta deformations then in finite group.
They're coming from theta deformations, but at the same time, there's, as I said, there's no escaping the kind of non-commutative phenomena that people normally associate with Q deformations, because already, like, I'm playing with this silly circle bundle over quadratic irrational non-commutative 2 torus that has this modular sort of this modular phenomenon that you see with Q-deformed complex Hopf vibration. It kind of doesn't matter at this point.
Mm-hmm.
I guess one of the interesting morals has been that like, yeah, the de Rham calculus is really darn special, and you just have to work generally. There's no escaping. You can't escape working generally and dealing with the misery. So I don't know.
Okay, thank you.
Thanks.
And so, are there any other questions from? I guess we had quite a few during the talk itself. And how? I mean, well, then I'll ask another question.
Sure.
So, coming from these objects, then I mean, is the idea somehow to build spectral triples from this algebraic picture?
So what's the big goal? The big goal is to I mean Edwin actually really said it. I mean, you have these sort of two solitudes. You have this sort of spectral action framework where in some sense you obviate the need to deal with any kind of principal bundles by basically setting up something akin to the adjoint bundle and just defining the spectral action directly. And then you have actually going into the weeds of setting up like all the bells and whistles of a gauge theory. The sort of algebraic picture, which at the same time poses analytic difficulties. So I guess in the paper with Bram, we started with spectral triples and unbounded KK theory, and we tried to nudge things in the direction of, in this direction. And I guess here, I think this is very much in the flavor of a lot of what Edwin and Majid have been up to. You're starting on the purely algebraic side and trying to shove things in the direction of spectral triples. So the hope is to build a bridge, to break down the two solitudes and to build a bridge. And this is entirely, I mean, Edwin basically said it. That's what the end goal is. One thing I will say is that, again, if you're working with spectral triples, it really privileges the first order calculus. And so if you're working with the de Rham calculus of a spectral triple, you can hack order 2. This is what Bram and Adam Rennie and Walter von Seilekum did in their paper on curvature. You can hack it, but then curvature, they have a definition of curvature that makes appeals uncomfortably many, for their sort of purposes, makes uncomfortably many appeals to the universal calculus. And so the question is, even if you're just starting with spectral triples, viewing a spectral triple as encoding the total space of a quantum principal bundle, can you talk about curvature of principal connections in a way that involves as few extra ingredients as possible beyond the first order de Rham calculus?
But then, I mean, if you try, well, this is again me perspective I would come up. I mean, if you look at not principal bundles in general, principal comodules, but look at quantum homogeneous spaces, so where your P is a Hopf algebra, then if everything that you do, your calculus, you have everything is covariant, then you can bring it across, because all of these vector bundles that you have, these principal bundles, would be induced or co-induced from a representation of H, a co-representation. Yeah. And then you can bring everything over to that category, and your life becomes a lot easier. You can.
Well, that's the thing. I mean, that's something you can only access if you have the quantum principal bundle in hand, unless I've misunderstood you. like, I mean, I guess one of the issues is
Okay,
is,
sorry, I see.
sorry.
Okay.
Am I making any sense?
Yeah. No, I see what you're saying.
And that again gets to this sort of difficulty that Edwin spoke to, where like when you normally do sort of gauge theory on spectral triples, it's really this ad hoc thing where you sidestep all the actual sort of machinery of a principal bundle and principal connections and gauge transformations, and just have this end result that that does the thing. But morally, what it seems to involve is basically skipping directly to the adjoint bundle, and then something that looks like a Yang-Mills action. But the sort of stuff you're talking about really involves having that underlying sort of classical gauge theory.
Yeah, sure. No, I misunderstood what you were saying earlier on, but yeah, no, I understand. Okay, thank you.
Okay.
Okay, so are there any more questions or? No? Okay, if that appears not to be the case, then we'll thank Branimir again.
Thank you very much.
And now we'll talk, next week's talk is again going to be more a non-commutative geometric as opposed to C-star algebraic. It's by Xiaoteng Wei, who's in Texas A&M Commerce. He'll be speaking about determinant line bundles and cohesive modules. So not so far from the general philosophy of today. The abstract is available on the website, and yeah, hopefully we'll see you all there next week. And thank you for coming.
Thanks, everyone.